Okay, greetings everyone. This is Dr. Shane from behind the camera here. And just letting you know a few things before we get started with our first lesson. So this is our first content-oriented lesson. And it's gonna take me, I'm gonna try different rooms, different formats to make sure that the lighting is okay. I already see that there's some glare on the whiteboard here. It may or may not matter. I'm actually recording this on a Saturday morning. Let's see, what's today's date? It is May 23rd in the morning. It's just a little rainy outside, so can't really do a lot of yard work or go out for a long bike ride. So here I am making some videos. So I'm gonna try some different things. So what's on the board in blue is probably not that legible because blue is not a great color. Black is about the best color, which I'll do most of the notes on. And what I did was I put the headings from the PowerPoint slides. So it's Roman numeral 1, and you can set this up on your own. I'm just doing this to get us into a rhythm here. So some things you're gonna want to have before we get started. I think it'll be useful. Now, what I'm gonna do, so I don't have to have a computer in front of me, is I'm just gonna print out the slides, and maybe you're doing that too, and I just print them out as a notes page. You can do that, and then you could just take the notes on these if you want to, or not. However you wanna do that is entirely up to you. Or print out the full slides and then just take notes on a separate sheet of paper, or just follow along with the slides as I set each bullet point up one by one, because I didn't write this whole slide on the board, just the Roman numeral major heading, the essentials and relevant chemicals and selected properties, because that's probably all I'm going to do with this particular video. So, and then I've got this image over here. So we'll probably work, this lesson might just be this slide, and that's fine. So just to get us set up. So where are we here? So, and we already did this in the intro video. This is chapter 1 of part 1, and we already went through this video with the thin blue line and looking at air quality. So you kind of know where we're headed. So I don't want to take too much time here. Some other things you're going to want to probably have available is, let's see, this is the problem set that has a bunch of references to sections in the OpenStax book. Okay, that's fine. I'm not going to read all of that to you, but you might want that handy in case you just want to do the review on a piecemeal basis, like case by case basis. And I'll write the sections in the upper right corner, so you might want that handy. There's a bunch of downloads on D2L that I just printed out again, so I don't have to have a computer with me. This is the table of bond energies, covalent bond energies. So you can look at that and have that handy. And what else? Well, you always have to have one of these. And I said, pro tip, print this out on a nice quality printer. What else? And the last thing are these tables of thermodynamic data, which is actually just a scanned photocopy from a general chemistry textbook, because it's a nice comprehensive list. If you find a better one online that's electronic, the only column we're going to need is this first column for enthalpy, delta HF. So the other ones we teach in general chemistry, but I don't think we're going to use those in this course, so we don't really need a ton of this table, but this is handy to have. So having all of that material either available on your computer screen or printed out like I have is fine. So let's go ahead and get going. You'll also want a calculator, and I don't think we're doing a ton of math with this lesson. So let's just give it a shot and make a video that's, we'll see how long it is. I've probably been talking too long. And okay, I'm gonna step out from behind the camera. So I've got my calculator, and hopefully this, I think I have the field where it's just the whiteboard and not a lot of stuff surrounding it. So we'll see how we do here. All right, so we are starting this first section on stratospheric chemistry, the ozone layer, heading essential. So set all that up however you want. Just do whatever works for you, and then I'll kind of fill in the gaps. And let's see if I can keep this fairly straightforward. And I'll probably write a little bit big. So we are underneath number 1, and this is letter A for what are the relevant chemicals that we're talking about. Okay. So let's sort of clear out some of the rust if you haven't had Gen Chem in a while. So one of the molecules we're going to talk a lot about in this course is diatomic nitrogen. You know that nitrogen on the periodic table is an atom, but when it exists in its standard state, under normal conditions that we would consider normal, it's a diatomic species, sometimes called a diatomic molecule, a diatomic atom, and it's also a gas. So we use the subscript there. And this is approximately 78% of the air that you breathe. So that's the majority of the air, because most species on Earth are bacteria that require nitrogen. Nitrogen serves a function in aerobic organisms and mammals like us, but it's not as necessary. And the book doesn't do this to the extent that I do it, but I think it's helpful to consider the chemical structure and how we get that. The book assumes that you remember how to do this. And what I would do is, I forget the specific sections of open stacks that talk about drawing electron dot structure, so I have to go back here and get my notes. I should keep these more handy. And the book does not reference, the first page of the chapter of the book does not reference this. And it's a big chunk, you don't have to do all of it, but open stacks sections 7.2 to 7.6 are worth reviewing. And if you read all the materials up to this point, is when you look at those sections, it's fine, you can just kind of skim them for what you need, almost use open stacks as a dictionary or an encyclopedia, just get what you need from it. And within those sections there are called check your learning problems and link to learning problems that are just quick things you can do to make sure you understand it. They give you the answer, a sample problem to try, and then if you need to, you can scroll to the end of the chapter and click on what are called exercises. Those are the end of chapter problems. Again, don't mean to insult your intelligence. And the odd numbered ones have the answers to them. You click on it and it gives you the answer. So if you need to kind of hunt and peck, if you will, for what you need to have this make sense. So nitrogen, when it connects to itself, has a triple covalent bond. That's what that is. And these are unpaired electrons, sometimes referred to as lone pairs. Again, this is not a Gen Chem class, but we need to understand that. And I think it's helpful to do this. If you look at the tables of covalent bond energies that I gave you, just to corroborate, you look this up, and the bond energy here is 941 kilojoules per mole. And I'm going to write out the word mole, M-O-L-E. So you may have to go back and remind yourself of what that means. And kilojoule is joule a unit of energy, kilo, 10 to the third, 1,000. So it's scale to be kilojoules here. Now that's a pretty high bond energy. That's one of the largest you'll see on that table. In fact, if you want to scan the table for other bonds that are pretty high energy. So that's a piece of data that we're going to need. This is not part of what they cover in the book, but nitrogen connected to nitrogen has a specific molecular geometry. It's a linear molecule, and it's also non-polar, which means it does not have any separation of charge like water does. Water is a polar molecule, nitrogen is not. That's not a huge consideration in this course, but I think it's good to actually do a little bit of dissecting of the molecule, if you will, before we consider its environmental implications. The other thing I'll mention here is, if you look at the thermodynamic tables that I gave you and find nitrogen, I think the table's organized alphabetically, I think. If you look up nitrogen gas, not liquid, I'm not even sure if liquid nitrogen is on there, and you look up what's called the standard heat of formation, so, or change in enthalpy, that's what that refers to. Again, if you need to go back and review this, those sections are 5.1 and 5.3. Yeah, so if you need to go back and review the thermochemistry problems, those are the sections there. So you can do that if you need to. And you can do that at any time. But when you look up the heat of formation, now the definition of that is how much energy is associated with forming that molecule from its constituent elements in their standard state. Well, nitrogen, it's already in its standard state. It doesn't come from anything else because that would be non-standard. So by definition, the heat of formation of nitrogen gas is 0 kilojoules per mole. And you know what? Now I'll use the abbreviation. So MOL is the abbreviation for mole. MOLE is actually the abbreviation for molecule. So we'll just go to kilojoules per mole. Okay. That's fine. Those are just some properties that will come in handy with this one. I'll just see if I can fit another one on the board here before I erase it. And if I'm writing too big, I might try to fit more on the board, but I think it's helpful to do it this way. And plus, then I can give you some time while I'm erasing to try it on your own. Okay, all right. Another molecule we're going to talk a lot about is the second major component of air, diatomic oxygen. O2 gas. I'll just cut to the chase here. That's also its elemental state. So the standard heat of formation is also 0 kilojoules per mole. You can look that up in the tables to verify that. This is approximately 21% of the air you breathe. That's a good thing to keep in mind. The air you breathe is about 20% oxygen. 21, okay, that's fine. That is a very important fact for lots of things we're going to do in this course. And oxygen is not a double bond, or excuse me, it's not a triple bond, it's a double covalent bond with 2 pairs of non-bonding electrons on both oxygens. This is also a linear molecule. This is also a non-polar NP, non-polar molecule. And looking at the bond energy here, it's not as strong of a bond. It doesn't take as much energy to break this bond as it does the nitrogen. It might stand to reason. This is a double bond, that's a triple bond. It just intuitively sounds like it's a weaker bond, and indeed it is. The bond energy there is 495 kilojoules per mole. Excellent, okay. I'm going to fit another one in on this board, and then when I erase it, I'll give you a couple more, and you can try them on your own to get ahead, so you're not just sitting here writing stuff down. All right, so another molecule we'll talk a little bit about, I just kind of tossed this one in here, is argon. It's another component. Now, if you look at the periodic table, argon is a noble gas. Used to be called the inert gases, would mean they don't react, but that's not 100% true. So those are the noble gases. They don't bond to anything typically. That's not 100% true. But argon is just a gas by itself. It's monatomic. It's not diatomic. It's monatomic. And this is about 1% of the air. The heat of formation of argon is also 0, and there is no bond energy because there are no bonds. So that's just to do that for contrast. Okay, I'm going to do so that was letter C, argon. I'm going to do D and E simultaneously. So D will be carbon dioxide, CO2 gas, and E will just be water vapor, H2O gas. So if you want to set up D and E and see how far you can get, do you remember how to draw these? Do you remember what they look like? And if you don't remember how to draw those, that will give you reason to go back and look at these sections. These are called electron dot structures. In fact, you can use the OpenStax textbook, and there's a search engine, and you can just type electron dot structure, and it'll take you right to that and show you the rules for drawing these. But take some time, and you can always stop the video if you want to. I just need a minute to erase the board. So, letter D, carbon dioxide gas. Letter E, water vapor, H2O gas. This gives you a little break of having to listen all the time too. There is such a thing as solid and liquid carbon dioxide, but those are pretty rare. Solid carbon dioxide you might know as dry ice. That's used to make for like a fog machine in theater or something like that. Let's see if we can do these side by side, because they're good for comparison. But if you want to do them on top of each other, because your notes are top down, not side by side, that's fine. I don't need to treat you as new students, you're not. And when if you're not sure what to do, if you look up these molecules on that table of thermodynamic data, make sure you pay attention to the state of matter. Sometimes you'll see 3 listings: solid, liquid, gas. Solid, liquid, gas. Make sure you look up the right one. Let's just start there. Let's just start with the easy stuff. It's looking things up on a table. The standard heat of formation of carbon dioxide in its standard state, which is a gas, I've got to find it, is negative, that's important, 393.5 kilojoules per mole. Might as well talk about this now. When you have a heat, the better term is enthalpy. Okay. Enthalpy and heat are synonyms under conditions where the pressure doesn't change, and that's typical for us. The environmental pressure, we're assuming only minor fluctuations in atmospheric pressure, so it's a good assumption. Anyway, the negative sign indicates an exothermic process. Energy is given out when this forms. Okay, so that's, you look that one, I'm just looking it up, make sure it's the right one. I think that's right, I don't think I would have made that mistake. Water in the gaseous state, the heat of formation, the standard heat of formation is also negative, but it's not quite as much, 241.826 kilojoules per mole. Again, when you go back and review this, if you need to review what those mean, these are the amounts of energy that carbon dioxide would take to form from elemental carbon and elemental oxygen. This is the heat associated with forming gaseous water from elemental hydrogen and elemental oxygen. So go back and review those if you need to. Let's see. Carbon dioxide this is a molecule we're going to talk a lot about. 0.04% of the atmosphere. However, if you know anything about global warming and climate change, you realize that carbon dioxide is something we pay attention to, and as the amount of carbon dioxide in the atmosphere increases, that becomes a concern. So this percentage is not fixed. It's not a constant. It depends on anthropogenic, man-made, human-induced, if you will, activity. So this number is from 2012, which is when your book was published. So that's variable. That is not a fixed number. Okay, and then, well, I'll just keep going back and forth here. Water vapor has a variable percentage because it's of the water cycle. So you have evaporation going up, precipitation coming down, and then all of those things you might have learned about in earth science about the water cycle. Okay, so we have all that information, the bonds. So I'm going to show you the result here. Carbon dioxide, you put carbon in the middle, symmetry is typical for these, and you have an oxygen on each side with 2 lone pairs on both oxygens and 4 non-bonding electrons. This molecule is linear. Again, it's not a huge important point for environmental chemistry, but there's no reason we can't go a little bit more. It's a linear molecule. It is non-polar. And if you look at the table, be careful when you look at the table. In the, I think it's the lower right corner of the table, the double bond in carbon dioxide has a especially high bond energy. The bond energy there is 799 kilojoules per mole. And it's also worth noting that it's not the whole molecule that has that, it's just one of those bonds. So the total bond energy for carbon dioxide would be 799 times 2, because there's 2 bonds. The same thing applies to water. Drop my cap here. Water is and you may have been hearing about this since middle school. You may instinctively draw water like this, because water is non-linear. It has a bent structure because of these 2 non-bonding pairs of electrons on the central atom. And that's stuff you might want to review, but it's not a huge deal for this class. It has a bent structure. What else do I want to say about it? It is a polar molecule. I wasn't going to do this, it isn't in my notes, but I'll add this now. So polar means that there's a positive part and a negative part. And that's based on the concept what's called electronegativity. Again, this is really getting into the weeds. And it's not a plus and a minus like an ionic compound, like sodium +1, chloride -1. It's only a partial positive or a partial negative, and we use the symbol lowercase Greek delta. Oxygen has a negative charge, slight negative charge, partial negative charge, and both of the hydrogens have a partial positive charge. That's what makes it polar. And let's see, the bond energy here, it's only a single bond between oxygen and hydrogen. You can look that up. That is just a standard part in the table. And the bond energy there is 467 kilojoules per mole. And the last one we're going to do, well, we better do it, is the title of the chapter, ozone. And I think I'm going to erase this. So ozone, the chemical formula is O3. You might have already known that. It's a gas. If it wasn't a gas, we wouldn't be talking about it in the atmosphere. So if you want to, why don't you go ahead and look up all that information. See if you can find the heat of formation. Okay? See if you can draw the electron dot structure. And see if you can take a guess about anything about how much is in the atmosphere. And that's actually a trick question, because there's no single answer to that one. It depends on where you are. And that is the key thing. It depends on where you are in the atmosphere. And indeed, what is the atmosphere? What does that even mean? And we have to break that down. Okay, so this will be letter F. This will be our last molecule. So we're not doing a lot of math in this lecture, so I don't think you really need your calculators, but give me a minute. So letter F, ozone, O3, subscript G. I'm not erasing very easily. Oh, I should get some paper towels. Okay, that's fine. I'm going to fit it in here. It doesn't really matter as long as you have it organized in your notes. So F. Ozone. O3 gas. I looked up the standard heat of formation. Oh wow, okay, this one is positive 143 kilojoules per mole. That means endothermic. That means you have to put energy into it to make ozone. That is an important fact. It's not just a number with a sign, plus minus. The fact that it takes energy to make ozone indicates that ozone is made in the atmosphere from something. Well, that something is oxygen and some other things too. So that is actually a really important fact. The structure of ozone. Oh, by the way, how much ozone is up there? Well, that is altitude dependent. So if you just want to add that in there, it depends on the altitude. And the rest of the graphics for this lesson, I'm not going to talk about those. It's just, they're just there. Okay, so it depends on where you are. And the last thing is the structure. It's not a huge thing to deal with, but I think it's kind of important to do. If you look at the structure of ozone, and if you can't figure it out, you can always just Google or say it into your phone, you end up getting, well, it's 3 oxygens. You get one in the middle with a non-bonding pair, and then you have a double bond on one side and a single bond on the other. And it's also bent. It's non-polar, they're all the same atom, but so you could write that, I suppose. But that's not a hugely important fact, but I think it's good to do. Now, you may also know, oh, let's get the bond energies here. I'm not going to write BE. Well, there's 2 different bonds, right? So it's 495 kilojoules per mole for the double bond, and 146 kilojoules per mole for the single bond. Now, that's actually not reality, because this electron dot structure, I could write it with the single bond on this side and the double bond on this side. I think I got that right. In reality, ozone is an average, which is called a hybrid, if you will, of these 2 structures. So it's really the average, and you may have seen this in general chemistry. If you've had organic chemistry, these are called resonance structures. So it's not this or that, it's halfway in between, if you will. And sometimes brackets are put around these. So the actual molecule is not a double bond and a single bond, it's a 1.5 bond in between those 2. And I think that's maybe where I will end. I'll try to fit this in, but how do you show a halfway bond? Some books will call it this. They'll go this, we'll do that, they'll do that, this, and this. So instead of putting the double bond here or here, they do the double bond sort of spread out throughout the remainder. I think that's sort of, it looks like a frowny emoji. I never really thought of that. But anyway, that's what we do there. Okay, I want to wrap up this first video because this is it's getting a little long and it's primarily qualitative. It's just information. So the last thing, and I'm not going to talk too much about this, is on the slides. There's a great image on there. So just go to that slide that has this and copy down the layers of the atmosphere. These are hugely important, but I'm not going to spend time writing this on the board. You can write this yourself. So number 2, wherever that went. So number 2, atmospheric layers. Just copy that information. What are the takeaway messages here? The troposphere is where you're standing up to about 15 kilometers. So that's ground level atmosphere, if you will. And you get about 85% of the atmosphere, of the mass of the atmosphere from that 0 to about 15 kilometers. When you go from 15 to 50 kilometers, 15 to 50, that's called the stratosphere. And that's where you see on that graph, there's a big temperature switch. So the temperature as you go up, 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 then, okay, you can see that on the graph. You get a temperature reversal because of a bunch of exothermic reactions, which we're going to go over. And then that's where most of the ozone is. It's not really a layer of ozone. It's just diffused throughout the stratosphere. And on the next slide, you simply see 2 graphics that are better representations of what I just said. In the troposphere, you don't have much ozone. In fact, when you come down to the ground level, the ozone that we talk about is anthropogenic, man-made, human-induced ozone that has health effects that we'll talk about. Ozone up in the stratosphere, which we need, is useful for blocking ultraviolet radiation, and that would make life impossible on Earth if we were bombarded with all that ultraviolet radiation from the sun. So the ozone has a lot of different functions in the atmosphere depending on where you are. If you will, ozone down here in the troposphere is bad for our health. Ozone up in the stratosphere is necessary for life. And then, then ozone, we're going to do some math with this one. That shows the absorption spectrum of ozone. What's that? that takes a chunk of the wavelength of the electromagnetic spectrum, the ultraviolet region of the electromagnetic spectrum in this case, we're going to do more of this next time, and shows you what wavelengths of light is it most efficient at absorbing. The takeaway here is that ozone is very efficient at absorbing ultraviolet radiation. And I think from there, that's where we're going to stop this video. The next video will be on general considerations about the electromagnetic spectrum and reminding yourself how to do some of the math, and also what does all that math mean when it comes to the environment. Okay, so I think that'll cover it. So we'll see you on the next video.